Welcome to Signals and System subject classes. Now we are in the 7th chapter, that is Laplace transform. So this is the second video in this chapter. So previously we have discussed about Laplace transform, its derivation, and how it is related to the Fourier transform, and we have done some problems also in the related to the Laplace transform. And compared to the continuous time Fourier transform, Laplace transform, it is having the special case, that is region of convergence. So here, this x of t, it is a continuous time signal. You should remember this Laplace transform, it is related to the continuous time signal. So this x of t, it is a signal. So it is a continuous. So actually in this class, actually we are going to learn inverse, what is the inverse Laplace transform, how to derive it, what is the importance of the inverse Laplace transform. So inverse, so in this inverse Laplace transform, so it is so Laplace transform, you know that it is related to the continuous time signal. So this x of t, it is a continuous time signal. It is a continuous time signal. So here this derivation inverse Laplace transform, it can be derived from the Fourier transform. So that's why here I would like to write this Fourier transform formulas. That is, in continuous Fourier transform, that is a signal in time domain, that is x of t. After applying continuous time Fourier transform, so continuous Fourier transform, so that is x of j omega. So the x of j omega, it is a Fourier transform of the x of t. So x of j omega, so that equal to integral of minus infinite to plus infinite. So x of t into e power minus j omega t into dt. So this is formula for continuous time Fourier transform. So now inverse Fourier transform, that is x of t. So x of t equal to 1 by 2 pi integral minus infinite to the plus infinite. So this formula is very, very important. With the help of this formula, we are going to define the inverse Laplace transform. So this is x of t into e power j omega t into d omega. So this is inverse Fourier transform formula. So before explaining the inverse Laplace transform, first we should know that Laplace transform, already it has been discussed in the previous class. That is good. So Laplace transform x of s. So we know that, so x of t, so x of t, so it's Fourier transform, Laplace transform, so that it is denoted by the capital X of s. So this x of s, capital X of s, it is equal to integral of minus infinite to the plus infinite x of t into e power minus st into dt. Now we have to derive the inverse Laplace transform from this concept and this inverse Fourier transform. So here I would like to tell about this relation between the Laplace and Fourier transform. Again, already we have discussed this relation. So here this x of s, Laplace transform x of s, it is equal to the Fourier transform of, see, Fourier transform of x of t, is it correct? For condition, so what is the condition here? That is the condition s equal to j omega or j omega, or it is equal to the x of, sorry, not like that, not equal here. Here, so here, whenever s is equal to j omega, so this x of s is equal to the x of j omega. Is it? So, so Laplace transform x of s. Now we are going to derive the inverse Fourier transform. So minus infinite to the plus infinite. So x of t, now I'm going to substitute. What is the s actually? S equal to sigma plus j omega. Actually, this is the relation between the Fourier transform and Laplace. Whenever s is substituted in s domain that equal j omega, it becomes the Fourier transform. That for that condition only, I have written this statement. But in Laplace, the s equal to sigma plus j omega. So e power. So here I want to write so s equal to sigma plus j omega, that equal to minus sigma plus j omega into dt. So then expand that power of exponential, that equal to x of t into e power minus, see here, sorry, I forgot, here this is t. So sigma t into e power minus j omega t into dt. So this is the signal in the time domain. That so x of s. So this is similar to the Fourier transform. See, this is integral of minus infinity to x something signal in time domain and is multiplied by the exponential e power minus j omega. Here also e power minus j omega into integration with respect to t. Here also t. So this is the Fourier transform. Fourier transform of this Fourier transform x of t into e power sigma t is nothing but x of s. So Fourier transform of x of t e power minus sigma t, so that equal to x of s. So that equal to x of sigma plus j omega. Is it? So x of here also it is we can write this is equal to the after substitution of the s equal to sigma plus j omega, that equal to x of sigma plus j omega. Here also it is equal to the x of sigma plus j omega. So now, so with the help of the inverse Fourier transform, I'm going to find the x of t. So inverse Fourier transform, what is inverse Fourier transform? This is time domain. So this is 1 by 2 pi integral of minus infinite to the plus infinite. So x of, sorry, this is x of j omega. Sorry. This is capital X of j omega. So this is x of j omega into e power j omega t into d omega. So it is equal to the x of t. So similarly, so this is the formula for the inverse. So inverse Fourier transform. So for that, so this is signal in time domain x of t into e power minus sigma t. It is inverse Fourier transform of 1 by 2 pi integral minus infinite to the plus infinite. So x of j omega. So this is the Fourier transform for the x of t. So what is the Fourier transform of the x of t into e power minus sigma t? So this is the x of s. So here this x of s, here I'm writing that equal to sigma plus j omega into e power j omega t into d omega. So we should know x of t. So we need to send to the this multiplication to the right side. So x of t here I'm writing directly 1 by 2 pi. So integral minus infinite to the plus infinite. So x of sigma plus j omega into, so send to the right side 1 by e power minus sigma t, then that goes to sigma for sigma t. So sigma e power sigma t, e power sigma t into e power j omega t into d omega. So 1 by 2 pi integral minus infinite to the plus infinite. So x of sigma plus j omega that equal to e power. So t is the so this is the a power m into a power n that equal to a to the power of m plus n. For that e power sigma t plus j omega t, and t is the common. So sigma plus j omega into t into d omega. So this is equal to the x of t. Now, I am assuming we know that sigma plus j omega that equal to s. So again, we should know the d omega. Now, I want to change the variable omega to the s. For that, have taken sigma plus j omega equal to s. So different. So here we should know the differentiation of the omega. So differentiate this one. So j into, so this is the constant. So d omega that equal to ds. So d omega that equal to ds by j. Then limits values. So these are the limits for the omega. So omega equal to minus infinite. For the corresponding s value, for the this value corresponding this value s that equal to s. So substitute omega value. So here the sigma, this is minus j into infinite. So this is the case. Omega equal to infinite. So s equal to sigma plus j into infinite. So in finally, so this x of t that equal to 1 by 2 pi integral sigma minus j infinite sigma plus j infinite. This is x of s into e power st. So d omega equal to what we got? D omega equal to ds by j. So finally, we can write so x of t that equal to 1 by 2 pi. So minus infinite to the plus infinite. X of s, sorry, j here I am writing here this j, 2 1 by 2 pi 1 by 2 pi j x of s into e power st into ds. So this is it is inverse Fourier transform. Sorry, inverse Laplace transform. Inverse Laplace transform. So I need to write in one place in one. So here this inverse Laplace transform, that what we got the formula that could x of t. So x of t equal to 1 by 2 pi j integral of sigma minus j into infinite sigma plus j into infinite x of s into e power st into ds. Is it? So, and Laplace transform formula is x of s that equal to integral minus infinite to the plus infinite x of t into e power minus st into dt. So these are the formulas. These are very, very important. So in similarly, we can write. So these are the x of t x of s. For the continuous time, see this x of t is derived from x of t equal to 1 by 2 pi integral of minus infinite to the plus infinite x of j omega into e power j omega t into d omega. So Fourier transform, this is x of j omega that equal to integral of minus infinite to the plus infinite x of t into e power minus j omega t into dt. So this is the case for the continuous x of t continuous time Fourier transform, that is x of j omega. So this is related to the Laplace transform relation between. Once you substitute s equal to j omega here, then you will get it becomes a continuous time Fourier transform. So for based on these formulas, so we derived some in last class. So we have done some problems. These are the basic formulas. So you should remember. Once these four are very, very important. Based on these four, you can do any problem. So try to remember. So here I will try to how to remember. See, so the first one, so e power minus at into e of t. E of t. So it's Laplace transform. So it's Laplace transform that equal to 1 by s plus a, and it's the region of convergence that equal to sigma. See, this is right sided. U of t, it is a signal which is having the magnitude from the 0 to infinite. Is it? So we should take the greater than minus a. Why we should? So this is the minus a. It's we have written from the formula here. We have the minus a. Further say minus a. So how did you get this formula in regional convergence? This is discussed in the previous class. If you have doubt, go back to seventh chapter, the first video, part 1. So our it is derived from the this formula, this x of s and so similarly, so e power minus of e power minus at. So u of this is left sided unit step signal. So it's Laplace transform. So both are having same Laplace transform. That is important thing. So 1 by s plus a, both are same Laplace transform. See, for this we got the same, here also same. But the region of convergence is different. Region of convergence, that equal to, this is left sided, so left sided. Sigma less than, so here we have the minus a. It will come here, is it? So for that, here we have taken the minus a functions. So in these next two cases, I will consider e power at into e of t. So for that Laplace transform. So for that Laplace transform, that equal 1 by here we have plus a, that minus of minus a. If you this is, we can write this is like minus sign minus, is it? Minus and minus. So then s plus minus a, it goes to minus a. So its region of convergence same. It is depending on the type of the signal, whether it is right sided or left sided. So this is the right sided. So right sided. So sigma always greater than here. This is a value equal to plus a. The last one minus of e power at left sided minus t. For this case, so it is also having same Laplace, that equal to 1 by s minus a, but the region of convergence, that equal to, so sigma, this left sided, so less than and a, sigma less than a. So what is the sigma actually? The sigma is nothing but real part of, yes, real part of, yes, there is a, so this is a about Laplace. Then we will do some problems based on this concept. The first one, so problems. So x of t, here I am taking x of t equal to sum of the two exponential, that equal, x of t equal to e power minus 2t into e of t plus e power minus 3t into u of t. So this x of t is the sum of the two exponential. Then, so what is the Laplace transform? X of s and region of convergence. Determine x of s and ROC. So this is I am assuming this is x1 and this one is x2. For that, Here I am writing this x1 of t that equal to e power minus 2t u of t. From this formula, so Laplace transform equal to x1 of s. So that equal to 1 by s plus 2. S plus 2 and region of convergence sigma greater than minus 2. And the second component x2 of t that equal to e power minus 3t into e of t, and so this is x2 of s, same 1 by s plus 3. Its region of convergence sigma greater than minus 3. So this x of t, so it's Laplace transform. So that equal to, so Laplace transform. So x of s that equal to sum of this 2 that equal to 1 by s plus 2 plus 1 by s plus 3. Based on linearity property, we will discuss the properties of Laplace transform in the next class. So, but what is the region of convergence? That is a question mark. Why? Because 1 plus s plus 2, we have written this is formula for the region of convergence that equal to greater than minus 2. For this one, sigma greater than minus 3. So, what we have to do? See, before that, here I am drawing the region of convergence of the individually. So this is minus 2. So this is sigma greater than minus 2. So this is sigma, this is j omega. So sigma greater than minus 2, so right side. The next one, sigma greater than minus 3. So this is minus 3. So this is a region convergence for the sigma greater than minus 3. So this is a sigma and this is j omega. So sigma greater than minus 3. So this is the right side. So this is region of convergence for the sigma greater than minus 3. The common area, which is common area? So this is sigma greater than minus 2 is a common area between these two. So here this region of convergence is nothing but sigma greater than minus 2. So this is the region of convergence. So for this, you can write like this. So this is sigma and j omega minus 2. This is minus 3. So this is sigma greater than minus 2 for x of s. So this is for x1 of s. This is for x2 of s. So this is the way to write a region of convergence for the sum of the two functions. So next problem. So next problem, the same similar problem. So on x of t that equal to e power for this case. For this case, I want to take minus e power minus 2t into u of minus t minus e power minus 2t u of minus t. Then determine x of s and region of convergence. So this is the case. So these two are left sided. So this is e power e power minus 3t. So we know that it's x of t. So Laplace transform that equal to, so already we know that. So 1 by s plus 2 plus 1 by s plus 3. So this is x1 and this is x2. So for the x1 of s that equal to 1 by s plus 2, its region of convergence sigma less than minus 2. Minus 2. So this is less than. So this is left side. This is sigma and this is j omega. Sigma less than minus 2. The next one, so this is minus 2 and this is minus 3. This is -2 and this is -3. Here also this is sigma less than -3. So this is the x-axis is sigma and this is imaginary axis j omega. So here sigma less than -3. In previous case, sigma -2. This is a common, correct. So from this common, so this x of s, so x of s, the x of s equal to 1 by s plus 2 plus 1 by s plus 3. So the region of convergence, so sigma, so the common area, so this common area sigma less than -3. This is the region of convergence for the x of s. Sigma and j omega. So this is for the -2 and this is -3. So this is -2 and -3. This is sigma less than -3. So another problem. X of t, so x of t equal to e power e power -3t into u of t minus e power -2t into u of t. Then determine x of s and region of convergence. So this is I'm taking this is x1, so this is x2. So we know that this x1 of t that equal to e power -3t u of t. It's a Laplace transform. So it's a Laplace transform that equal 1 by s plus 3 and the region of convergence sigma greater than -3. Now it's a region of convergence. Here I would like to draw the region of convergence. So this is -2 and this is -3. Sigma and j omega, this is region of convergence for the sigma greater than -3. So for that, the next one, the second component, that is so x2 of t that equal to minus e power minus 2t. Sorry, this is u of minus t. This is left sided actually. Minus t. So e power minus 2t into e of minus t. So Laplace transform. So that equal to 1 by s plus 2, but the region convergence is less than sigma less than -2. So for this case, this is -2. We want to take a different color. So what is the common area? So the common region of convergence for -3 to the -2 is the common. So we can write this x of t. So Laplace transform, that x of s that equal to 1 by s plus 3 plus 1 by s plus 2. So the region of convergence. So region of convergence for these, first. This is -2. This is -3. So first, sigma less than -2. Next one, sigma greater than minus 3. So this is the so region of convergence, it is from the minus 3 to minus 2. So this is the region of convergence. So this is a common region of convergence. If any signal having some of the two component. The last problem. So last problem. So one x of t that equal to e power minus 2t u of t and minus e power minus 3t into u of minus t. Then determine x of s and region of convergence. So this is x1, this is x1 of t, so this is x2 of t. So this problem is very important. This problem is very important. What is the difference from the previous problems? Just observe it. So x1 of t that equal to e power minus 2t into u of t. It's a Laplace transform. So it's a Laplace transform that equal to x1 of s that equal to 1 by s plus 2. It's a region of convergence. It's a right sided. So sigma greater than minus 2. So the region of convergence, um, I'll write in one diagram. So x2 of t, so that equal to e power, sorry, minus e power minus 3t into u of minus t. So it's Laplace transform. So Laplace transform. So x2 of s that equal to 1 by s plus 3 having that sigma. So this is left sided, so less than minus 3. Now here I would like to draw the region of convergence for the common. So if before common, I would like to draw individually. For that, so this is j omega, this sigma. The first one minus 2. This is minus 2. And this is minus 3. So first write minus 2 region of convergence. So this is region of convergence sigma greater than minus 2. Next sigma less than minus 3. Let's draw the line. Then so sigma less than minus 3. So this is the left side. So this is region of convergence for the second one. This is sigma less than minus 3. So in this case, so we cannot write the common region of convergence. The common region of convergence does not exist. Then we cannot define the Laplace transform for this case. So here, so x of s, see x of s cannot be determined for this x of t that equal to e power minus 2t u of t minus e power minus 3t into u of minus t. Why? Because there is no common region of convergence. So this is the case. It's very, very important. So these are the related to the region of how to. So the Laplace transform it is defined based on the region of convergence. These are very, very important. So this is Laplace transform. Then in next class we will discuss some more problems. Thank you.